Hello everyone. In this lecture, we are going to discuss the second type of inferential study done on proportions, and that is to perform a hypothesis test. Previously, we talked about the inferential study on proportions, which was to estimate the population proportions by creating a confidence interval. Now, here we are going to devote the time to discussing hypothesis test as applied to proportions. We will not go into the concept behind hypothesis tests because that has been discussed in a separate lecture. We are going to just focus on the step-by-step process of performing the hypothesis test for proportions, like how we state the hypothesis, the distribution we use for our test, the specific formula to calculate the test statistic, and then of course using the two approaches of critical value and p-value to arrive at a decision, and finally how we interpret the results of the hypothesis testing. Now, before we look into the step-by-step procedure of performing a hypothesis test for proportions, let's spend a little bit of time going over the purpose of a hypothesis test. Now, in any hypothesis test, there is an established population parameter. It could be the population mean or it could be the population proportion, but it is the parameter that has been generally accepted to be correct, to be true. Now, a recent study has perhaps come up with its own results from a study on a sample, and they want to contest the established parameter and reject it. That is the goal. The goal is to reject the established population parameter and replace it by the results of a more recent study. However, in order to do that, there is a process. The decision whether it should be rejected or not rejected has to be based on some criterion, and for that there are two different approaches, a critical value approach or a p-value approach. But whichever approach is used, if the results of the sample study, in other words, if the evidence provided from the sample study is strong enough, then based on the approaches used to perform the hypothesis test, a decision can be taken to reject the established parameter in favor of the alternate measurement that was obtained from the sample study. All right, so that is essentially the purpose of a hypothesis test, to replace a well-established population parameter by the findings of a more recent study. And that being said, now we are going to go over the step-by-step procedure that one should follow to perform a hypothesis test on proportions. Now, here are the steps of performing a hypothesis test on proportions. There are 6 steps in all, starting from stating the hypothesis all the way to interpreting the results of the test. However, on this particular slide, we have just 3 steps, and then in the next one, we will talk about the remaining steps and the approaches we use for the study. Right? Now, this procedure is called the z-test procedure because any study on proportion uses the z distribution. We saw that also when we were learning about the estimation of population proportions using confidence intervals, we use the z-distribution. Similarly, for hypothesis test, we are also going to use the z-distribution, and that's why it's called the z-test procedure. Now, this is a one proportion z-test. Later on, we will also learn about the two proportion z-test where we compare two proportions. But for this lecture, we will be focusing on one proportion z-test. The purpose is to perform a hypothesis test for a population proportion P. As with all other tests, as well as confidence intervals, we have to make sure certain conditions are satisfied. The first being that the sample that is used for the study is a simple random sample. And secondly, specific to proportions hypothesis test on proportions, both n times p sub 0 and n times 1 minus p sub 0 are 5 or greater, which means that the sample size multiplied by the population proportion, p sub 0 represents the population proportion. So that should be given to us in the question. So we have to take that proportion uh, of the null hypothesis and multiply it by the sample size, and also do the same here for 1 minus p sub 0, and both these values should be greater or equal to 5. Now, these assumptions being satisfied, we can proceed to performing the hypothesis test, starting with step 1. The first step is always to state your hypothesis. You have to present your case before you can start contesting the uh, null hypothesis. The null hypothesis is written in this form, in notation form, H sub 0, 0 implying null hypothesis, colon, P equals P sub 0. So for stating any hypothesis, we should always use the population parameters. So it should be P, and do not use P hat, all right? Because that implies sample proportion. So P for population proportion equals, null hypothesis should always have an equal sign in its statement, is equal to P sub 0 is whatever the population proportion is stated to be, and the alternative hypothesis denoted by H sub A implying alternative, is stated as colon P, again the population proportion, not equal to P sub 0, which would make it a two-tailed test, or it could be a left-tailed test where it says the population proportion is less than whatever the null proportion is, or P is greater than P sub 0, which would make it a right-tailed test. So alternative hypothesis can be one of these three statements, all right? It could either be not equal to, less than, or greater than, one of these options. Once the null hypothesis has been stated, we go on to deciding the significance level alpha, which decides the criterion to come to a decision. All right. Now, for our course purposes, the significance level will be given to us most likely in percentage form. We have to convert it to decimal and write down its value, or take its value alpha. Alpha is a value between 0 and 1. All right. Step 3 is to calculate the test statistic which is obtained from the sample study. So compute the value of the test statistic. It's going to be a z value because we are using the z distribution, and the formula for it is p hat. So here the first time we see the sample proportion getting used. So p hat, which is going to be obtained from a sample study, minus p sub 0. So what it's checking is how far the sample proportion that was obtained from the study is off from the null hypothesis proportion in terms of a z-score divided by square root over p sub 0, again null hypothesis proportion, times 1 minus p sub 0 divided by n. This is also the formula for the standard deviation of proportions, correct? So that is the test statistic that, or the evidence that we bring to the table in order to complete the rest of the hypothesis test. So in the next slide, we will discuss the approaches that we will take by building a criterion to come to a decision whether the null hypothesis can be rejected or not rejected. And then, of course, we learn how to interpret the results of the test. So we discussed the first three steps of the hypothesis testing procedure for proportions. The first one was to state the null and alternative hypothesis, then to decide on significance level, and the third one was to compute the value of the test statistic, which is essentially the evidence that we bring to the table to come to a decision on the null hypothesis, and that is derived from a formula, right? We looked at the formula for that. In step 4, we apply the approaches, the two approaches to come to a decision. Now, the first approach is called the critical value approach, and then there's the other one, which is a p-value approach. The letter P stands for probability. All right. So in the critical value approach, we take the value of the significance level alpha, and alpha is typically going to be a value of either 0.01 or 0.05, or it could be 0.10 as well, but typically 0.05 is used as a significance level. And what this alpha value does is it creates regions on the standard normal curve. Since for proportions we are using the z distribution, these curves are all standard normal z curves, and we use the value of the significance level alpha to separate the curve into two regions, reject region or the do not reject region. And this alpha value is going to decide where the cutoff is going to be between the reject and the do not reject region. Where on the curve the reject region is going to be placed, where the reject region is going to fall, in other words. And that cutoff point, which is going to be a z value, right? On a z curve, the horizontal line has z values with 0 being located at the center point. So the critical value essentially is going to be a z value. Now, if it is a two-tailed test, then the reject region is going to be on both ends of the curve. A two-tailed test, which actually comes from an alternative hypothesis statement which says not equal to, correct? It comes from the not equal to symbol in its statement. And that's what makes it a two-tailed test. So when we say that the population proportion is not equal to the null hypothesis proportion, we are essentially saying that it could be less than what the stated proportion is, or it can be greater than. So there's a possibility it could be less or greater. It could be on both sides of zero, or either side of zero, not both sides, but either side of zero, right? In that case, the reject region would be on both ends of the curve, and the region in between the two reject regions, the two ends, is going to be at the center. All right, in between the two is going to be the do not reject region. And there are going to be two critical values. A negative value is going to be the cutoff on the left hand side between the reject and do not reject, and on the right hand side it's going to be a positive z value. And the alpha value in the case of a two-tailed test, the alpha value has to be split into two. All right. Now, recall that the alpha value is also the area of the reject region, because the alpha value is the probability of making a type 1 error, correct? Therefore, the alpha value represents uh, the area of, or the probability of, the reject region. In a two-tailed test, you have to make sure that you split the alpha value into two equal parts. So we start with the significance level alpha value. First, we use it to find the z value, the cutoff points, the critical values, and then we draw our curve and show where the critical values are. If it's a two-tailed test, in the case of one-tailed test, a left or a right-tailed test, we do not need to split the alpha value. We just find z of alpha. If it is a left-tailed test, the z of alpha is going to be a negative value. If it is a right-tailed test, then it's going to be a positive z value. And then once we create our criterion of reject and do not reject regions, we will bring our test statistic uh, that we computed in step 3 and see where it falls. If it falls in a reject region, then we will reject the null hypothesis. If it falls in the do not reject region, the decision is not to reject the null hypothesis. All right. So in summary, the critical value or in the critical value approach, we start with the alpha value to find the critical values or the cutoff points between the reject and the do not reject regions. And then we bring our test statistic value and see where it falls in our diagram here. If it falls in the reject, reject. If it falls in the do not reject region, the decision will be to reject, as simple as that. All right. As for the p-value approach, we start with the test statistic we found in step 3. We find the probability of getting a test statistic value that we found, assuming that the null hypothesis proportion is true, right? So we start with the test statistic value and we place it on the standard normal curve. All right, we place it on the standard normal curve. There's no reject or do not reject regions applicable in the p-value approach. Do not mark regions with reject and do not reject for p-value. All you do is bring your test statistic. You see over here z sub 0. Z sub 0, this represents the test statistic value. All right. So you show it where it would fall on the curve. And if it's a left tail test, then find the area to the left of the test statistic value. All right. If it is a right tail test, then find the area on the right hand side of the test statistic value. If it is a two tail test, then show uh, the negative. Let's say that we have a positive test statistic value. Make sure you show the negative counterpart of it as well on your diagram. If it's a negative test statistic value, make sure you show the positive counterpart of it on the right hand side. And find the area on one side, and then you have to multiply it by 2, double that area that you found on one side. So start by finding the area on one side, and then for a two-tail test only, you have to double that value, multiply it by 2. And then once you do that, once you find the p-value, which is nothing but the area representing the probability, you compare that with your alpha value. So in the p-value approach, we see that the significance level comes at the very end of the approach. The role of the significance level alpha comes at the very end, unlike with the critical value where we start off with alpha. All right. So if P is less or equal to alpha, then we take the decision to reject. If P is greater than alpha, then we do not reject the null hypothesis. All right. So look at step 5. If the value of the test statistic falls in the rejection region, reject null hypothesis. Otherwise, do not reject null hypothesis. By the critical value approach, that's step 5. By the p-value approach, the step 5 is comparing p to alpha. If it's less, reject. If it's greater than, do not reject. And finally, step 6, where we interpret the results of the hypothesis test. And that will bring the test to a conclusion. All right. So after this, we are going to work through an example applying each of these steps using both approaches, critical value approach and p-value approach, and then taking a decision and finally interpreting the results in context of the question. All right? Here is an example on which we are going to apply the steps that we just learned for performing a one proportion Z hypothesis test. Now I'm going to first read through the problem because most of the problems in statistics is going to be word problems telling a story, and it is important to understand what the problem is about, understand the question that we have to answer, and then of course we will extract the data from the verbiage of the question. So this particular problem is to do with economic powerhouse. It says a national poll of 1,015 randomly selected US adults asked which country is the leading economic power in the world. Of those sampled, 538 said China. At the 5% significance level, do the data provide sufficient evidence to conclude that a majority, which would be greater than 50% of the population, believe China is the leading economic power? So apparently, a survey was sent out to 1,015 US adults asking the question who they consider, that means which country they consider to be the leading economic power. And of those that were surveyed, 538 thought China was the leading economic power. So the question that is being asked here is to perform a hypothesis test to conclude whether the majority of the entire population also believe that China is the leading economic power, whether the sample study is true for the entire population, right? So I'm going to first go ahead and extract the data from the verbiage of the question. Now, it always helps if you have the formula that you will need, whether you're performing a confidence interval or finding a confidence interval, or whether you are performing a hypothesis test. If you have the formula before you, it will help you know what data you are looking for. Since this is a hypothesis test, I'm going to write out the formula for the test statistic, and that is going to be, and let me write it up here, z sub 0, which represents the test statistic notation, is going to be p hat minus p sub 0, which is the null hypothesis proportion, divided by the square root over p hat times 1 minus p hat divided by n. All right, so this is the formula to find the test statistic, and let's extract the relevant data with which we can solve this equation. All right, we are not going to use the data right away on this portion of the lecture, but this is going to help us determine what data we need. So this formula has n, or the sample size, in it. So let's find out what the sample size is. 1015 randomly selected US adults are to whom the national or to whom the survey was sent out. So this represents the sample size. So n is going to be 1015. All right. What does x represent? All right. Well, the formula doesn't have x in it, but we need to know what the sample proportion is. And in order to find the sample proportion, we need to know x, because the formula to find the sample proportion is x divided by n. What is x? X is the number of respondents that replied yes in the affirmative to the question. All right, so 538 said China, so x is going to be 538. So I'm going to write here 538. I'm listing all my data. Next we have p sub 0. P sub 0 represents the null proportion, the null hypothesis proportion, in other words. The null hypothesis proportion is going to be 0.5. All right, because over here it says a majority, which represents greater than 50%, but that means 50% would be the percentage for the null hypothesis. All right, so 50% has to be converted to proportion, which is going to be 0.50. 0.50. So this is what is the null hypothesis proportion. Well, the null hypothesis proportion has to be a decimal value, so we have to convert the percentage to a decimal value. And then p hat, which is the sample proportion, is going to be obtained from the formula x divided by n. So we know x is 538 and n is 1015. And when we perform that division, we will come up with a value of 0.530. All right. So now we have pretty much the data that we will need to perform our test, right? The next step is to check the assumptions so that we can apply the procedure, right? The assumptions for the proportion test are two. First, it has to be a simple random sample, and I'm going to write SRS for simple random sample, and that is given in the question itself, randomly selected US adults. So this phrase randomly selected tells us this is a simple random sample. Data was obtained from simple random sample. So that condition is met here, is satisfied. The second condition was that n times p sub 0 and 1 minus n times, n times 1 minus p sub 0 both should be greater or equal to 5. So n is 1015 times 0.5 is of course greater or equal to 5. And the other one is 1015. Now 1 minus 0.5 here. 1 minus 0.5, p sub 0 being 0.5, 1 minus 0.5 is also going to be 0.5. So 1 minus 0.5 is also going to be greater or equal to 5. Therefore, both conditions have been met, have been satisfied. Now we can go to stating the null and alternative hypothesis. Null hypothesis, let's write it in notation form, H sub 0 colon, and then you always use the population parameters. So you're going to write P, no P hats when stating the hypothesis. So P is equal to, null hypothesis will always have an equal sign in it, is equal to what is the population proportion of the null hypothesis. It's 0.5. So we are going to write here 0.5, and that's the null hypothesis. The alternate hypothesis is H sub A, and then colon, and then P. Again, it's still the population proportion, because the question says we have to conclude whether it is greater than 50%, the sign is going to be the greater than symbol. All right, it's going to be the greater than symbol, so greater than 0.5. Okay, so that is our hypothesis statement. And then it says decide on the significance level. That value for alpha will come to us from this 5% significance level, the measure at which we are conducting the test. And at the 5% significance level, of course, alpha is going to be a decimal value, so we have to convert it into decimal. 5% is 0.05. Now note that this is going to be a one-tail test because we have the greater than symbol. In the alternative hypothesis, it's going to be a right-tail test. So I'm going to make a note of that as well. It's going to be a right-tail test. So by the critical value approach, the reject region is going to be on the right side of the curve. All right. So in the next slide, we will go through the next few steps of calculating the test statistic, applying the approaches to come to a decision, and then interpreting the results. Over here, we are going to find the test statistic, which is the third step of the procedure. All right. Now I've brought over the data that we listed and calculated in the previous page. So over here, n, which is the sample size, was 1015, x 538. Then the null hypothesis proportion, p sub 0 is 0.5, and the sample proportion was calculated as 0.530. All right, so this is all the data we will need to plug into this formula to find the test statistic value. So let's go ahead and do that. Now, test statistic is always indicated with a subscript of 0, in this case z sub 0. So let's just go ahead and plug in the values, and then we will do the calculation. So p hat is going to have a value of 0.530, right? So I'm going to write here 0.530, then a minus sign, and then we have p sub 0, which is the population proportion of the null hypothesis. So that's minus 0.50, 0.50 divided by, so this is all z sub 0, divided by the square root, and make sure you are writing out the formula correctly. This square root goes over the entire numerator and denominator of the formula. All right, so we are going to write p sub 0 is 0.5. Again, that is the null hypothesis proportion, times 1 minus 0.5 divided by n. All right, so what is n? N is 1015. So 1015. And when you are plugging this into your calculator, make sure that you are following the order of operations. Don't try to do the entire calculation in one line. It's better to break it up into steps. That means first find the value of the numerator, then calculate what the denominator is, and then do the division. That way it'll be easier for you to make sure that the calculation is correct. So 0.530 minus 0.50 is 0.03 in the numerator, and when we do this calculation of the denominator, we come up with a value of 0.015. So 0.015, and then do the division, which is going to be 1.911. All right, so that is the test statistic value, the test statistic value. All right, so let me just highlight this, because we are going to have to use this in the next step, which is performing the test using the critical value approach and also the p-value approach. First, we are going to conduct the hypothesis test using the critical value approach. Later on, we will also talk about the p-value approach, but at this point, I would like to focus on the critical value approach and explain the steps for it. All right. Now, in a critical value approach, we separate or divide the standard normal curve, in this case a z curve, into regions: reject region and a do not reject region. Now, if it's a one-tailed test, a left-tailed or a right-tailed, then the reject region will be just one reject region, and then there'll be one do not reject region. If it's a two-tailed test, however, the reject region will be on both ends of the curve, so there will be two reject regions and then the do not reject regions at the center. But this was a right tail test, if you recall. So it's a right tail test. Let me write that down. And how do we know what tail type test it would be? It's determined from the alternative hypothesis. The alternative hypothesis of this problem said that p is greater than 0.5. Correct? So that made it a right tail test. And the other thing that we need to note is what the test statistic was. The test statistic that we found in the previous step was z sub 0 Z sub 0 was equal to 1.911. It was a positive value. All right. So now we are going to draw our curve showing the reject and the do not reject region. So let me go ahead and pull up a standard normal Z curve. All right. So here is our curve. Here's our curve. Again, we said the reject region is going to be on the right hand side. So at this point, I'm just going to draw a line separator, a vertical line on this curve. All right. And at this point, we are going to mark the right hand side as the reject region, and the left hand side is going to be the do not reject region. All right. We don't know what the whether this cutoff between the reject and do not reject region is correct or not at this point, but we know for sure that the reject region is going to be on the right hand side of the curve. That is important. All right. How do we know what the cutoff point is on this Z scale? All right, where it should be, whether the line should have been drawn here or at this point or even more to the left, we don't know. All right, so that will be determined from the alpha value. So keep in mind, what was the alpha value that we are using? It's a 5% significance test, so alpha was 0.05. So the critical value, the CV, or the critical value is Z of alpha. All right. So Z of alpha is Z of 0.05. Now you can look up the table, the Z table, and you should find a value of 1.645. That is the critical value, the cutoff between the reject and the do not reject region. So maybe it should be a little bit to the left. All right, it's a little more than, I guess it doesn't matter, but let me just move it a little bit to the left, be a little more accurate. All right, so if it's a little more than 1.5, so maybe it wasn't that wrong. So here we have our line, and let's mark that as 1.645. That's the critical value. All right, 1.645. That's the critical value. So the critical value, CV, I'm going to write that again, and you need to show all your work on your assignments and tests. So just write it. What is the critical value? It's Z of 0.05, and you can look up the table and see that it's a value of 1.645. All right, so once we know what the critical value is, the next step is bring your test statistic and see where that falls in this curve. Z sub 0 is 1.911. So I'm going to write here, all right, Z sub 0, which is the test statistic value, is 1.911, and that is greater than, all right, 1.911 is greater than 1.645. So 1.645, and in a right tail test, that is going to fall somewhere to the right of 1.645, somewhere here probably. This is where 1 point, little bit to the left of 2. So let's write that down. All right, it's going to be 1.911. It'll be a little bit to the right, maybe here, I don't know. Right, if this is 2, then over here. Anyway, it does fall in the reject region, correct? 1.911, the test statistic value, based on the cutoff of 1.645, it falls in the reject region. So you have to write that as well, showing your work, because we want to see whether you understand the approach. So falls in reject region, reject region. Therefore, your decision will be reject null hypothesis. Reject the null hypothesis. That would be the decision based on the critical value approach. All right. And then, of course, we have to go and interpret that, but I'm going to perform the test using the p-value approach and see whether we get the same decision as we got with the critical value approach. Let's perform the same test now using the p-value approach, and we should arrive at the same reject null hypothesis decision as we did with the critical value approach. Now, in the critical value approach, we started with our alpha value. We used the alpha value to come up with the critical value indicating where the reject region and the do not reject region on the curve would be. And then we brought our test statistic to see where that would fall, where that test statistic would fall relative to the critical value. And if it fell on the reject region, we rejected it. If it were to fall on the do not reject region, then we would take a decision to not reject the null hypothesis. On the p-value approach, we start with our test statistic. All right, so let me go through the process again. Whether you're using the critical value or the p-value approach, a diagram is necessary. The standard normal curve is going to be brought up here. So here I have the standard normal curve, and I'm going to write the value of our test statistic because that's what we are going to begin with in the p-value approach. So the test statistic was z sub 0 equals 1.911, correct? So what I'm going to do now is I'm going to show where 1.911 is on the standard normal curve in this diagram here. 1.911 is going to be a little bit to the left of 2 standard deviations, z of 2. So I'm going to mark that somewhere over here, and that's where 1.911 is. And again, there's no reject and do not reject regions in the p-value approach. Do not show reject and do not reject regions. It's not applicable for the p-value approach. But just show where your test statistic would fall in the standard normal curve, and I'm going to extend that. And then the next step is, for a right tail test, find the area to the right of where the test statistic falls, because in the p-value approach we are trying to find the probability of obtaining the test statistic value of 1.911 given that the null hypothesis is indeed true. All right, so we are looking for the probability of obtaining a 1.911, and that's why we call it the p-value approach. P stands for probability. We are trying to find the probability of obtaining a test statistic value of 1.911, assuming that the null hypothesis is still located at the center of the curve, that it is true. So you're going to find the area to the right of this value of 1.911, because area and probability essentially mean the same thing, correct? So find the area. So we are looking for the area to the, find area to the right, to the right. Now because it's a right tail test, we will find the area to the right. If it were a left tail test, then of course your test statistic value would be located somewhere on the left somewhere over here, and you would find the area to the left. That would be your probability value. This is a right tail test, therefore we are interested to find the area to the right of 1.911. And if you're using the table, then the table will give you the area to the left. To find the area to the right, you have to subtract this area from 1, correct? Now the area to the right, well, let's first find the area to left. To left of 1.911 is 0.971. So all this area is 0.971, but we are interested in this area to the right, right? So you have to subtract 0.971. Therefore, area to the right is 1 minus 0.971, and that should be a value of 0.029. So what we just found was the p-value. So p-value, the probability value, is 0.029. So that was the first step. In the second step, you're going to compare the p-value with alpha. So compare p-value with alpha. So in this case, it's 5% alpha was equal to 0.05. So you're comparing 0.029. Is it, the question you're asking is it less than the alpha value of 0.05? Yes. All right. So is p less than the alpha value? In this case, the answer is yes. If p is less than alpha, the decision is to reject. If it is less or equal to alpha, then we reject the null hypothesis. Yes, therefore reject the null hypothesis. And that decision is the same as what we got from our critical value approach. And that's how it should be. Both approaches should arrive at the same decision, right? Now we are in the final steps of the procedure. We have to formally state the decision and then write out an interpretation. Now there is a format to interpret the results of the hypothesis test, and I'm going to write it out and tell you about some of the critical verbiage that you must include in the interpretation. But for this particular problem, the decision was to reject the null hypothesis, and make sure that you have explained the reason for the decision when you perform the critical value approach and the p-value approach. All right. For the interpretation, we are going to start with stating the significance level at which we perform the test. So we are going to say at the 5% significance level, always qualify your test with the measure at which you perform the test. So at the 5% significance level, the data provides, so the data provides sufficient evidence. Now, if you have rejected the null hypothesis, then your data was strong enough, the evidence was strong enough to reject the null hypothesis. So you're going to say it does provide sufficient evidence to conclude, and then you have to state the interpretation in context of the problem. It's not enough to say it provides sufficient evidence to reject the null hypothesis. You have to write the interpretation in context of the problem, but you can pick that verbiage from the question itself. It says over here, do the data provide sufficient evidence to conclude that a majority? Just use this verbiage, all right? You don't have to think about how to phrase it. Just pick up this verbiage and write it down. So to conclude that a majority So I took a pause and wrote out the interpretation. So the critical phrase over here is, of course, at the 5% significance level. So this part of the interpretation is very important. You have to qualify your interpretation with the level at which you perform the test. And then if it was a reject, you are going to say the data provides sufficient evidence. If it was a do not reject, then you would say the data does not provide sufficient evidence. All right, so this is important, whether it provides evidence or doesn't provide evidence. Again, for reject, your data was strong enough to reject the null hypothesis, to overthrow the null hypothesis. If it was do not reject, then you have to say the data do not provide sufficient evidence. And then you have to write the rest of it in context of the question. And my advice is just use the verbiage in the question itself to conclude that a majority greater than 50% of all US adults believe China is the leading economic power. All right?